All right, this is our last installment of the Plant Phys Primer. And in this last section, we're going to be talking about nutrients. And so I'm going to really use nitrogen as our example for nutrients. And some of the other nutrients, it's a little bit different than it is with nitrogen. But for the most part, the concepts we're going to be talking about with nitrogen apply to any nutrient. All right, so when I'm talking about nitrogen, kind of in your head think, oh, this applies to these other nutrients that plants are getting from the soil as well. So when we think about kind of how plants are using nitrogen, we use the term and we think about nitrogen use efficiency. And there's three main components to nitrogen use efficiency. How fast plants can take up nitrogen from the soil, how they're used for growth once they get that nitrogen. And really we're talking about how much photosynthesis can they do for the amount of nitrogen they take up. And then lastly, we have the residence time of nitrogen inside the plant. So you can almost think about like once an individual atom of nitrogen gets into the plant, how long does it stay in the plant and get reused? Because it's not just used once and discarded. It can kind of be reallocated to different types of jobs, or it can be reused over and over for the same job. And so it can stay in the plant and be useful for a long period of time. So we're going to talk a little bit about these three things. So let's first just look at a very broad scale relationship between net photosynthesis and leaf nitrogen concentration. So this is the weight of nitrogen in the leaf relative to the weight of the whole leaf. That's why it's milligrams per gram. So that's a concentration. And then we've got our photosynthetic rate up here. What you see is this positive correlation. The more nitrogen a leaf has, or the higher concentration of nitrogen in a leaf, the faster that leaf is going to be able to do photosynthesis. And we already talked about this. It's because Rubisco relies on nitrogen, or a plant relies on nitrogen to build Rubisco. And so the more nitrogen it has, the more Rubisco it can build and the faster it can do photosynthesis. In this case, all of these symbols represent different species. So we're not talking about one species in different concentrations. We're talking about comparing different species. So we know plants that are going to photosynthesize fast also need lots of nitrogen. So let's first talk about the rate of uptake. So the most important factor in understanding how fast plants can take up nutrients from the soil is understanding the structure of their root systems. And so if we can contrast the two most drastic different types of root systems as we have here, we've got a tap root, so carrot might be the most drastic example of a tap root. And then we've got this really fibrous root system where the roots branch off into smaller and smaller pieces all along the length of the root. This root system is going to be really poor at taking up nutrients quickly. So it's going to have a slower nitrogen uptake rate or nutrient uptake rate. And that's because there's relatively little surface area here. Even though it's a big root, if you add up all of the surface area, it's not that much, especially compared to this fibrous root system. If we were to go through and measure the surface area of this fibrous root system, we'd find that it's a lot more surface area than taproot. So this is a really good root system for producing lots of surface area. That surface area is important because the main component in taking up nutrients is just having your root come in contact with a nutrient. And the more surface area you have, or a plant has in the soil, the more likely it is to run into those nutrients and be able to take those nutrients in. So plants want a root system with a really large surface area. Now you could imagine going through and measuring the entire surface area of this root. Or maybe you can. If you can imagine it's a lot of work. You'd have to know the diameter and length of every single section of that root, and then you would calculate the area of each section and then add them all up. And it would be laborious and miserable to actually do it. So we've come up with a metric. I didn't come up with it. Somebody came up with a metric to kind of do a good job of estimating the surface area of the root relative to how much biomass the plant had to invest in that root. So it gives us an idea of how much surface area there is in a root system relative to the amount of energy the plants put into it. So we talked about carbon budgets early on. This kind of gets back at this carbon budget issue. How much carbon do you have to allocate to your root system? So what we have is this variable we're going to measure, or we're going to talk about, is specific root length. So it's the length of the entire root system, still miserable to measure, but better than surface area, and the dry divided by the dry mass of the entire root system. That gives us the relative length of the system relative to the biomass investment. So let's just talk about an example. Let's say we have two different root systems. So these drawings are supposed to represent two root systems. This, each one of these lengths of the root system is 1 meter, and the mass of each section is 10 meters. So if we were to calculate the specific root length, we got to draw. For this one, we would have 3 meters, the length, divided by 30 milligrams. All right? And so we could do 3 divided by 30, and that should give us 0.1. So that would be the specific root length for this one. This root system over here, again, each length of the root system is 1 meter, but each section weighs 100 milligrams. So in this case, we have 3 divided by 100. And this gives us 0.01. All right? So the one on the left has a higher specific root length. Relative to how much biomass it invested, it has a lot more length. And you can kind of think about it that it builds longer but cheaper roots than this plant on the right. But in general, a plant that uses less carbon to produce a longer root or more roots is going to be able to explore the soil better and more thoroughly and have faster uptake rates. And so we would guess that this plant on the left has higher uptake rates than the plant on the right. There's one problem, not problem, but there's a trade-off. Actually, let's do this. I might type it because you can read it better. All right, the trade-off. Cheap roots don't live as long. So a plant that builds these roots, they're not going to last very long in the soil. Some roots only last hours long, and then they're gone. Some roots can last, the entire lifetime of a plant. But if you build lots of these, they're not going to last long, and you're constantly going to have to be kind of replenishing your root system. So that's the trade-off. They uptake nutrients really fast, but they don't last very long. Okay, so that's the first part of, that's the first part of the nitrogen use efficiency, is the rate of nitrogen uptake. The second one is the efficiency of the nitrogen, how it uses it for growth. So there's several different ways that plants can utilize the nitrogen once they take it up from the root system. Some plants just store it. There's a number of plants that just take up nitrogen or other nutrients and store them and never even use them. And we think this is a mechanism for competition to prevent other plants from getting those nutrients, and we refer to this as luxury consumption. So when you measure the concentration of nitrogen in a plant, not all of that is actually being used. Some of it might just be stored. Another way you could use the nitrogen is allocating it for photosynthesis, primarily rubisco. So if a plant takes all of its nitrogen, or the vast majority of it, and puts it towards rubisco, that plant's probably going to photosynthesize really fast. But there are other physiological processes a plant might need to allocate the nitrogen for. Actually taking up nutrients requires nitrogen. Stressful conditions tend to use lots of nitrogen. Plants might need to use nitrogen for their defenses, especially chemical defenses. And so because of these several different uses a plant might have for nitrogen, its nitrogen use efficiency could be really high, meaning it does lots of growth relative to how much nitrogen it has, or it could be low. It might actually have relatively low photosynthesis because it's using its nitrogen for something else. So just to give you some insight into this, here's a paper showing an evergreen versus a deciduous tree and the nitrogen use efficiency. So in the x-axis, we have this nitrogen concentration. So low nitrogen concentration on the left. So these leaves have very little nitrogen. The ones on the right, those have lots of nitrogen. And then we have the photosynthetic capacity or photosynthetic rate. What we see is if we look at a single point, let's look at 0.1, we can see that the evergreen, represented by the closed symbols, has lower photosynthetic capacity for that nitrogen concentration. That means the evergreen has lower photosynthetic nitrogen use efficiency. That means it's using its nitrogen for something else other than growth. All right, so it's not necessarily a bad thing. It's just understanding how a plant is using the nitrogen. So I just want you to be aware that there are differences in plants in not only how fast they uptake nitrogen, but how they might utilize that nitrogen. Some are using it for growth, some are using it for other things. And there are lots of reasons that this photosynthetic nitrogen use efficiency would differ among plants, and it gets down into some really nitty-gritty cellular level processes. But again, the take-home message is that plants that invest more in the structure and the robustness of their leaves, they tend to have lower nitrogen use efficiency. They tend to have lower photosynthetic rates per unit nitrogen, meaning they're using their nitrogen for something else. Plants that build these really cheap leaves and they're only going to hang on to them for a very short period of time, they're allocating all of their nitrogen or the vast majority of it to growth. Okay, and then lastly with nutrients is the residence time. So again, we've got how long does an individual atom of nitrogen stay in a plant and get reused. One of the easiest ways to think about this is just to, again, think about evergreen versus deciduous trees. So leaves are staying on the tree for really different periods of time. The picture on the right shows some black spruce up in Alaska. These trees can keep their leaves for up to somewhere around 20 years. So one needle will stay on that tree for 20 years, and so the nitrogen in there keeps getting used over and over again for many, many growing seasons. Contrast that with the deciduous tree. This is a red maple starting to senesce its leaves in the fall. We know they drop their leaves every year, and lots of nitrogen falls to the ground in those leaves. And so it's just not keeping the nitrogen in those leaves around for as long, and so that's going to reduce the residence time. It's a less efficient way of using the nitrogen. It may work for that tree. It's not to say it's a bad strategy. It's just less efficient as far as how it's using its nitrogen. The other component of residence time is how much of the, or what percentage of the nutrients are resorbed out of the leaves before they're senesced. So this figure shows the resorption of lots of different nutrients: carbon, nitrogen, phosphorus, potassium, calcium, magnesium. I'm going to just focus on nitrogen because that's what we're focusing on right now. And what we can see, I'm just going to compare this A and this C for initial comparison to start thinking about some differences. These letters that you see here, or sorry, not these letters, but if we go down here to these letters down here, you can see it says Köppen A, Köppen B, C, D, E. You've already calculated the Köppen climate code for some data. And the very first letter in that Köppen climate system is what they're representing here. So if you remember, A is tropical, B is arid, C is temperate, D is continental, and E is polar. So let's just compare, let's just do A and C to start with. So tropics versus a temperate climate. So the tropics has relatively low resorption efficiency, so it's somewhere around 50%. That means 50% of the nitrogen in a leaf is taken back out of the leaf before the leaf falls to the ground. B, a temperate system has higher resorption efficiency, about 60%. So that means 60% of the nitrogen is resorbed before the leaf drops. That means it can reuse that 60% again next year, whereas in the tropics it's only about 50%. So, this resorption efficiency can change for different types of systems. If you look at B, the arid system, it's even higher than the temperate system. And generally what we see is plants growing in harsher environments tend to have greater resorption efficiency and greater nitrogen use efficiency. They operate more conservatively with their nitrogen. Once they take it up, they hold on to it tighter. What I want you to know now is that these two components contribute to residence time, and plants that tend to be in more stressful environments tend to reuse their nitrogen better, more efficiently. And that's kind of stated here. So plants with greater nitrogen use efficiency generally grow best on low fertility soils or stressful environmental conditions and take up nutrients at lower rates. And plants with low nitrogen use efficiency, on the other hand, generally grow in places where there's lots of nutrients, and they can take up nutrients really quickly. And if there's lots of nutrients around, it probably doesn't make sense to be really conservative with the ones you've taken up, because that just takes energy to resorb them and store them and then move them around next year. It might just be easier to sell it, get rid of it, and buy new ones the next year. All right? Okay, so that's our take home, or that's our kind of overview of the physiology of nutrients, and that concludes the Plant Phys Primer Part 2.